This is a breadboarded example of a constant current mirror. So let's look at the schematic. Essentially, a constant current mirror uses three identical transistors and shares their base voltage as well as the emitter configurations so that whatever current is flowing through one of the transistors collector will be the same amount of current flowing through the other two. And you can chain as many transistors on here as you want. The transistor on the very left will actually set the value of the current because there's an adjustable resistor here. This little shunt resistor is a very low resistance resistor, about 10 ohms, for me to measure what kind of current is possibly flowing through here. So something you might notice is without the shunt resistor, you might be thinking, well, if the collector is shorted to the base, isn't the base collector voltage the same? And therefore, this PN junction is not reverse biased, and therefore it's actually not going to be in the active mode, in the active region. It's going to be in saturation, essentially. But that's actually why there's a feedback in the first place, is because it forces, there's a little resistance in the wires, right? So the collector is going to be always slightly higher voltage than what's fed into the base. And that actually, no matter what the load is, will force this transistor to be just below the saturation region. Another thing to note is that in this diagram, when I wired this up originally, I didn't use these emitter transistors. So these sort of emitter degeneration resistors, sorry. I didn't wire those up, but when I didn't use them, the current fluctuated very wildly. In fact, the errors started compounding as the more stages I added. And that's because even though they're manufactured by the same manufacturer, the gain of a transistor is not exactly the same. So sometimes it'll be like 100, and then this one might be like 110, this one might be 120. And they also have different HFE gains depending on how hot they are. And because of that, if you relied just on the RE of the intrinsic resistance of the emitter, the gain can vary wildly, and therefore your currents won't actually be stable. In fact, when I did my setup, the voltage, the current that I was measuring started increasing as time went on. And I think the reason is because as the transistors heated up, their gains were actually changing, and so it wasn't actually a stable configuration. So some of them were drawing more current than the others. It'll be interesting as a future exercise to see why the currents were increasing and not decreasing. Because a hotter transistor, does that let more current through, or should I let less current through as they get hotter? But anyway, so adding the emitter degeneration resistor stabilized the transistor gain, and it reflected whatever current was going through this left-hand side transistor to the same to the second and third transistors. So if I turn on the voltage, which I set at 5 volts, you can see that the LEDs are on in the same brightness. And if I go and tweak this potentiometer, you can see that the brightness of the second and third one will actually change. Hopefully that picks up on the camera. So if I turn the potentiometer, so it's increased in brightness, and this is dimmed in brightness. Increase in brightness, dimmed in brightness, and they're the same brightness. What's more obvious is if I decreased this voltage, the supply voltage, even further. So if I decrease it to 4 volts or 3 volts, You can see that it's dimmed quite a lot, and if I change the potentiometer now, you see yep, they're the same brightness. And essentially the power output of LEDs, which determines their brightness, is the voltage across them times the current. And in forward bias, the voltage is always going to be about 2.2. So as long as you got the same current going through both of them, they'll be the same brightness. And if you want to calculate what the reference voltage on the left side should be, it's very simple. This shunt resistor, we can just ignore it because it's such a small resistance. And essentially, VB will actually be VC here, and VC is just going to be whatever this this voltage drop plus the voltage drop across the voltage drop across the emitter plus the voltage drop across the collector resistor is equal to the supply voltage drop. Because the transistor is kept very close to saturation, the voltage drop across the transistor is going to be negligible. So therefore, if you have a look at the equation for the voltage across the so basically VRA, the voltage drop across the adjustable resistor on the collector, plus VE, which is the emitter voltage drop, is going to equal to VCC. And if you don't have a resistor for emitter degeneration, VE is just going to be 0.7 volts, which is the p-n junction drop from the base. So 0.7 volts plus VRA, and let's say I have a VCC of 5 volts. So then VRA is going to equal to 5 minus 0.7 volts, and therefore if we divide both sides by the resistance, which is RRA, I've put the potentiometer as a 0 to 1K. So if we, let's say, put a 500 ohm resistor, then we got VRA divided by RRA, which will give you now the current through the adjustable resistor, which is the collector current, will then give you 4.3 volts over 500 ohms, which is, I guess, roughly a little bit less than 10 ohms. So let's say it's like 10 microamps. So it's about 9 microamps. Cool. I hope this was useful to somebody. The tricky part for me was really just trying to figure out, when I build the circuit diagram without these emitter resistors, how come the current was so different? And that's because you really do need emitter degeneration to match the currents in a current mirror. Great.